Elevation 12'9". Elevation 2'6". This is the original drawing, right? That's 1'6" now. This is no longer 1 foot 11-inch step up, but it's an 11-inch. It went from 1 foot to 11 inches. Let's go ahead and look at that detail, kind of like this. This will be the 111 room, so 111. And then let's drop down 7 inches. That stayed. And then we come out 11. We come out 11 feet. This one comes out 7 feet. All right, right there. So the first pad comes out 7, and then the second pad comes out 11 inches, 7, 11. And we have the tie-in to the existing pad. This is existing pad out here, the pool deck, all right, PD. So let's just do the PD here. And let's look at this beam detail, and that would be BMAs. All right, so BMA. Okay, let's go ahead and let me draw over here to your right. And I'm going to do the profile like that. All right, over here they have right here's a detail. Shows the L-shaped bar like that, and here again, L-shaped bar, as you see right there in that little circle. So it has to go engage into this beam, all right. But our deck is already determined. Our height is already locked in. It's let's call it 9.5 inches in our thickness here. Or is that 9 foot 5 inches, not 9.5? Okay. So our beam deducts from that. Our beam deducts from that because we have a composite action going on. Not 1 foot 11 step up, but it's going to be 11-inch step up. So 11 inches is here. So we get to add our 9.5 inches down below. Let's do it like that. And now for this, I'm going to go like this to make this little drop beam detail. Now it came up short there on purpose. I believe this beam detail, all right, so it came up short on purpose. So let's go. I want to show you that remember the L shape has to tie into this top part of this beam. It doesn't tie down into the structure like that. It ties, I think, flat like that. So there are hooks, and I'll show you another. I found a precast, show you an image of that, but right now just play along. So these hooks, I'm taking liberty by having it turned down. It's not turned down, I don't believe. So the integral part of this upper deck becomes integral with this beam like this. Okay, like that. This is the pour, all right, the pour up to it, making a cold joint here, cold joint here, like that. Okay, so this comes down, this beam like that, the BMA. That would be your BMAs across here. Okay, across the face. And then this one comes over and does the same thing. Now, that has to be supported somehow. So on this one, they probably did do like that and then pour this part secondarily. On the top one, the cold joint is what I'm talking about. We have a cold joint here and a little piece there. Okay, let's just think about that. So let's come back over here and look at this. On this side of the deck, you see the way it ties in to the BMA. All right, the BMA goes this way. The full BMA, I'm going to erase that now. The last one. All right, so that means it side mounts into the BMA, into the beam. So any dropping of the deck here, twerks the BMA to pull it off. Same thing with here. Any dropping of the deck out here, rotates that beam, that BMA. Okay, it's tied to the side here also. Okay, so it twists and rotates it, pulling it from the bottom like anchors at the bottom, pulling it like rope. All right. The top being stationary at the top. Oh, that because of the top steel, the angle top steel anchors it into the deck and allows that rotation better because it's anchored with the whole slab back to the structure. So that gives you that rotation to straighten it out. Okay, so I'm doing that as it pulls away. It straightens it out flat. Remember one of the images I showed you where the excavator, the excavator goes through the pad and makes it flat, and we see some exposed rebar right about there. I want you to just think of that exposed rebar as showing itself being at one point straightened out. Not by the excavator pushing that pad back and pushing that BMA back, but by part of the rotation of the deck going down, rotating the BMAs, twisting them in that capacity. There's nothing at the bottom side of this BMA. So here's the top part, and here's the bottom part. There's nothing on this side anchoring it, to stopping it from that rotation. So there's no counter anchor back here, down here. There's none there. So you got the anchors here that can contribute to the rotation. And so that would look like the real world like this. There's that 7 foot, 7-11. So 7 foot, 7-11, and then 11 foot. If I'm right, it's 7-11 with a 7-inch step up. So there's 2 7s and then an 11. And there's our core sample here. So there's your step up like that. Okay, let me go like this, take a little liberty there, and then let me close it up for you. That's your BMA, this part right there, the one I closed up. So that's that pulling action, can pull on this one, rotating it, anchored up top here, and flattening it back out. Let me do better than this. So over here you see another detail again. So this is just a curb, but it goes over to there. It goes 11 and back there. Okay, so I'm going to do your anchorage again. I'm going to take some liberty a bit and close that up and make that there. What I want you to see is it probably looks like this when they built it. Or maybe like this, like a shear link. And then like that. So the concrete probably initially went to there. And that was exposed up top, this little section here. And the rebar came over, it turned L-shaped, not down, because the concrete's closed off already, all right? It's sealed up. On the base, they might have engulfed, ready to form it up like that. And then this becomes the pad up to it. Developing rebar is out here and inside here. Okay, and this creates a cold joint there. Cold joint's okay, except for deflection. Deflection, if you don't have any top steel here going into here, then you don't have anything to support this when it starts deflecting. You don't have anything to counter that deflection there. The bottom steel doesn't counter it well. All right, most of that bottom steel is in compression, and it doesn't have the resistant force to, let's change colors on that, to stop that deflective deck action. And over here is our core sample, where the core sample was done, and we see the separation of the concrete and the core sample and the rebar. I state that that's through deflection that we're getting that. And when it deflects, you're getting this steel anchored here, back to here. And the deflection happens, and the fracture happens upon the steel. All right? It's not typical. It's not normal. It is normal in a deflection, as we see over all these years. That's a normal for that steel to behave that way. It is not normal to core sample and find steel and rebar all broken up apart from each other, unless it's the structure's suffering, if you will. Suffering. Failing. So we have the bottom steel there, but we don't have the top steel engaged like that, do we? As we look at an old image, hey George, as we look at an old image here, we see the walkthrough that this is that cold joint, right? So I'm going to remove it, that little fracture line. That's your cold joint, your step backs, or here, your step ups. Well, the step up is here. Let's change colors for you. It's here. That's just helping you visualize it with the pipe. And so this is that 11-inch step up. But remember, the 11-inch, it still needs to thickness of the deck, which is 9.5 inches, right? 9.5, 9.5 inches. So 9.5 inches. 9.5 is actually 9'6", so I don't think we're there yet. So it's 9.5. I mean, yeah, that's good. It's 9 and 9. Yeah, 9.5 inches. That's what we came up with. There's multiple thicknesses there, layers, but 9.5, I think, is the total thickness they were doing there. For the slab, for the structural slab. 9.5 inches is actually 9 inches, 1/2 inch. Right? 9.5 inches. So there's 9.5 inches. I think it was more like 9 5/8, 9 3/4. I did the damn core sample when I broke it up and measured it, location of the rebar and all that. All right, so the BMAs. Look at this BMA. If you're looking at the BMA here, I'll find an image of it again, but you'll see that it's slender here and then turns up. It's a little bit thicker there. So this is what it looks like, the BMA. So above this BMA here, I believe, are your links that tie your deck in, your shear links that they extended up and made composite action with the deck. So when the deck gets poured on top, it becomes like that, creating a cold joint right about there where the two of them meet. So that would be right there, a cold joint. A cold joint. Remember, I saw those the rebar sticking out like that in one of those images I presented. That would be probably the BMA with the 90 sticking out. That when it went down, we see the 90s are probably still engaged in the BMAs with this sticking out still. That'd be to the right of us. The right of us, but not over to the column, because we can't, the door's in the way of the column, so it's got to be concrete that we're looking at, the BMAs with with this detail sticking out. Wish I could find that image again. So as you observe here, there's the 11-inch step up. This is the 1'6" now, so this is the reduced from 2'6" to 1'6". Same thing here. This is the same deal going on, where the pad ties into the BMA. Let's do that BMA like that. I'm sorry, at the wall there. This is that 1'6". It's a drop slab detail. It ties in. So you're getting your cold joint probably here and here with your rebar, doing something like that with that one. And the top one, it's probably shear linked, and then coming across with the deck composite. So the deck from internal here probably goes out to sits on top of the beam, making a composite action. So little shear links like that. No cool joint presented there, but presents at the bottom here, so right about there. That would be observed out there if we could only see it. If we could only observe it, 7 inches is right below the deck. It probably was observable if you could see the before they put that topping slab on, with the tile up top of here. All right, so 11 inches here, 11 inches here. So there's a 7-foot step out, 7-inch step down. Okay, so we have a 7-inch step down there. Over here we have a 1'6" step down. So you can see the behavior is going to be different from left to right, from right to left. As it gets towards the building, it's going to have to do some rotation and pulling and yanking, kind of torque-wise, right? Remember this deal I showed you? So at this point, it's going to want to pull down and rotate the BMA that's going across. Okay. So and then when it gets to the structure, it only has it's reduced from, here's 1'6". It's elevated. The deck is elevated by 11 inches higher. So it's going to grab it in that BMA at a much higher point. Okay, so 7-inch step down here. It's going to grab it at a much higher anchor point than over here, for example. The deck is at 1'6", elevation change. So it's going to grab it. Here's 7 inches. Let's see if I get this right. This will be 1'6". Over here, it's going to grab at 1'6". Over here, it's going to grab higher in the BMA. The beams are going, the drop slab beam detail that goes across the face of the structure. So it's going to behave a little bit differently, grabbing at this section over here with the 7-inch step down, compared to over here with the 1'6", right there. I'll box it in, compared to 7-inch. Of course, this would be like the as-built, because this is the surveyor's rendering. Over here we have this fracture that identifies itself because the planter box stays exactly in place right here, right? Over to the doorway, you can see you can walk into the door if you could. So that takes place that way. Here is a planter box with the palm tree that you can still see with the branches standing vertical. The steps are probably solid poured steps. Maybe there's some fill behind it, I don't know. These are steps over here with the landing. Okay, so there's the steps there with the landing coming out from here. So when you exit the stairwell, you come out into the landing, and then you go down steps to put you onto the deck and then evacuate the building. No gate over here, sorry. Gate's over here. So this is your egress. the steps being solid would help out to a degree, but maybe also all that extra weight created it, along with the car weight, created this fracture plane right there. Remember, the car weights are here. Car loading and planter box. But that fracture exists, the one in red there. Okay, and then to the right, we have our core sample right here that I just tapped on. There's our elevation change. So we have a 1'6" elevation change over here. Over here we have a 7" step down elevation change. Back to 1'6" over here. So 1'6", 7, and 1'6". And then here, 11 inches. And a step up. So you got a deck plane here. It's one elevation, same elevation. But at this point, it changes to, yeah, it's 11, 7, 11. It changes to 11" step up. And then it's 7 more inches into the deck. So part of that wall structure, that BMA, this BMA at the wall, if you will, the elevation change, the drop slab detail, does have a pad on it. And this pad is approximately 8 inches or 9 inches. Let's just call it 9. So there's 9. Here's your 7. All right, so here's your total of this guy. And you see it run around the rosy a little bit there. That's about 1'5", 1.5 inches. And it's 1'6" on the one to the left. So it almost comes out in the wash, except for they used the, except for this is greater. This is 1'6" step up. So 1'6", you then add the pad 9.5 inches. So this is actually 1'6". It's a step up into the structure now. This is lobby area, if you will, lobby floor. Okay, so you actually add the 1'6" and the 9.5 inches, and you see where that's much greater than this. This is 1'5" inches, and this is well exceeding that. Here's 1'6" plus the 9.5 inch pad. So you're getting a larger, even though it's 1'6", you're getting a larger, this area here. This what I want to call an elevated plinth beam. You can call them tie beams. But they were supposed to be 2'6", not 1'6". So there's a huge difference in getting some rigidity out of that. So again, looking at the surveyor makes it clear this is 1'6", 7 inches, 1'6". These are steps, remember, in planter box. Core sample. There's your 11 inches back here. So, and here's your 11 inches over here. And this is 7, 7, 11. So, okay, so this is 7 foot. This is 11 foot. 7, 11, 11. So it's only 7. 7 here, 7 foot step up, 7 foot deck over here, 11 foot out, 11 foot down, 11 inches down. Core sample's way out here. This is just a curb, all right? So way out here is where deflection is taking place. It is in our critical shear zone, which you could argue is deflecting down in that capacity. Now this gets pretty strong inside here because of the action that you get from this beam here, this beam here, the beam here. So you're getting some strong rigidity floor here theoretically, but core sample says clearly that right here you're not getting that with the core sample being toothed, if you will. It looks like a bad tooth. It looks really separated like that when it's turned on the side, as you can see. If we turn it back up, it would be, let me see, so the chairs, it would be there. So and then this is a fracture plane of it together, 100% fracture planed. All right, and it didn't look like it just fractured because of vibration when they were cutting with the diamond blade, because it's pretty worn here. Like I said, looks like grinding teeth. So like deflection took place up and down, and that deflection would be between your supports. All right, here are your supports, the closest supports. So this is our deflective. Okay, this here it is here. Our deflective zone. Our weak spot is here. A low spot is there, dipping, deflecting, and causing that break I talk about when you load. That I'm telling you that it's a shear break that takes place when the direct deflects. The steel can only bond so much, and then it breaks. Breaks bond, and when it breaks bond over the years, it showed that it had a lot of elasticity to it, back and forth, and grinding on that sample. Now here's the proof of the L shape right here, the L bar, and that's coming from the pad internal to the drop slab detail. So there's that slab internal, and there it is. There's the L shape right there. It's like because some of them you could see the shear links. All right, so that cover was just ripped off, along with fractured. During that deflection, it was able to stress it so much that, just like you see in load testing of beams, where it would just abruptly acutely fracture the concrete and burst it off of the rebar. Well, this rebar is in L-shaped form still, so that shows that deflection took place. So that same type of failure took place, where it was so loaded that the concrete just fractures off. All right, it just fractures off. Literally, it's not made up. It's really, literally does that. You can see it's not even bent that rebar out of shape at all. And so you can take a moment to look at that 90, and think about the pouring mechanism, the pouring procedures. And so that beam was done. Looks like that's extended out, and then it engaged into the floor. Remember how they had it engaged into the floor in the BMAs. So the engaged into the beam, and then the floor is tied to it on this side also. Okay, so let's do that. So probably double crisscrossing like that, coming from the floor. This is the floor where the cars are right here. It's on the ground. If we can get on the ground, we might see some of that. We might also see the rebar going across, and that we saw in the middle, where it goes across. But this is at the structure, at that glass door structure. So this has a different detail over there where we see the steel going across. That's all floor. This has that drop beam detail. All right. And this is what I'm referring to as a drop beam. I think they refer to it as a slab drop detail. So I believe this is the other structure that I have an image of to help you visualize it. We're looking at it from the back side as if we were driving down the garage floor. This is just a visual of that of the drop slab detail, drop beam, as I also refer to it as. And so here it is here. So, and here's a column. All right, so above us here in this black is the pad going back towards us. Going back towards us. And this pad would be whatever it is, 9 inches. All right, but it just doesn't sit on top of here like that. There are some probably shear links that are sticking out, and when this pad gets poured, it engages. All right, let me pause and get that video on my phone. So on the underside, this, I believe the cold joint is, since we don't see a cold joint here for the pad, we don't see it here, unless they skimmed this whole surface here, which I don't think they did. The underside is right there, where the pad continues down. Okay, so that's where we get our 90s coming in and turning. Possibly when they built the pad, these drop slab details beam, that they put those 90s engaged in that direction. Remember, on this side we have nothing. So when this twists, when this pulls, this would be the lower part pulling, and it's anchored at the top. So it'd help it rotate, tearing from here. All right, tearing from there. Okay, I don't know how far they go out. And again, this is the other building. This just gives us a detail from the back side of it. Here, I found this image. Maybe this will help you see the setbacks. If you look over here, there should be this detail. See, it's not over there. That one's set back to there. So this is just showing you setbacks. Okay, so like that. And remember, the anchorage at the bottom, anchorage at the top. This going out here first would turn this, would torque it. Okay. Over here is where I say, I think it's New York Times, I say they're off because these aren't the same size as over here. This is larger. Remember, this is 1'6". Yeah, okay. This is 1'6" plus the floor thickness, 9.5 inches. This is 7-inch step down, floor thickness, and the floor thickness of this. And you would add the floor internal, but I would add the floor over here also. Yep, I'd add the floor here, so this would get it. So these two cancel each other out. Design-wise, they don't, because it's probably the shear link deal like that. They allow this exposed. I gotta find you an image for that. So you can see that over here, this is not continuous. Let me move it. So this is not continuous like they show this. All right, it's different sizing. Like you can see that one's different. This is 1'6". 1'6" is right here in this section here. And then this is your 7-inch plus floor deck, internal floor deck. And the floor deck outside thickness, not to be confused with the greater thickness of the floor deck, external slab, and the 1'6" difference in elevation. As they step this up, this got smaller here. So it just lost 11 inches right there. This will be 11 over here also. This now becomes 7. So they reduced this. This is reduced in size. This wall BMA right here, this beam, the beam that acts for rigidity across here is reduced in size compared to out here. Okay, let's see if I can wrap this video up now. So that's what I want you to see, is that this is 1'6". These are 7 inches respectively, 1'6". So this is not what they look like, but this gives you an idea of what it would look like. So the concrete goes on top, and then you engage. These are just hangers, hooks. See them? Just hooks. Whereas they would really be shear linked over and down. They don't show that here, except for in this drawing. You can see that it is shear linked on the detail. And up here, these hooks, this hook design. I don't know where this is going, this design, so I don't know the intent of their engagement, their hooks. It makes them get the development length, but it's so much, sweeter if you can just lock it down all the way over like that. Now, look at the H-beam, as it's known as before. You'll observe the H-beam, if you look at it before they went at it construction-wise, when the NIST was there and when the Army Corps of Engineers was there, you can see the pad on top of that H-beam like this. When they gut it, they remove the inside, including the pad. You all of a sudden see right here, you'll see all the stirrup system still in place where it engaged the floor. It shows you just the way they did their design technique, engaging the floor similar to this, making a composite H-beam, composite decking with the beam. So two more things I want to make sure I point out. So right here is where I talk about that pad. So your two pads are represented here. This is that steel in the middle. I talk about the being rotated down, pulled down, then they just scrape at it, and you're looking at the stirrup steel, probably inside that BMA that's like this, where the floor elevate changes right there. It's probably right there. Let me clean this up. Okay, so that's your floor engulfed all the way in front of on the ground, and there's your surface water there. So that pad did make it over to the structure, coming down, and it didn't. So we can't see from here, right, because of the door. But now we can see the pad where we can't see it, and we don't see a fracture pad like this hanging up like that. Looking for a fracture here, right about there. We don't see that. So the pad went flat over to the structure, pulling that off. So I know this is a tough one to look at, but meaning visualize. But this is that white coating that's on the H-beam, as you guys know it as. It's configured much different than H-beam, but excuse me. Here's the concrete flooring, right? That's the level of the flooring. And I'll move this in a minute, but you'll see right there is where the white stops in plane, where they broke it off, and it was easy to shear right there where it ties in. Noteworthy is this steel that ties in from the decking into the BMA. This H-beam, I was able to find out the details of that, but this one looks like it's about as best I can do for you right now. So this is some rendering I did, dinner table, obviously, at one point when I was out. And I'm just showing the 7-inch, the 11-inch, trying to add the math up, your core sample. And then, I think I said hooks on. Yeah, on this one, turned a little sideways. I should have shown hooks in that capacity, in that version. So same thing here. So imagine a formwork was put up. The Falseworks formwork was put here. This is the plywood, okay? It supports plywood, supports plywood, supports. And then he had this concrete deck on top. The concrete deck does not have tile on it at this point. And they run it right over top. This is going to be the concrete deck. I'm going over top of that wall to the left, as you may notice. Okay. And I'm going to add the rebar in there for you. And they lay down a rebar mat. And this way, the rebar crisscross like that. I showed you that in another video. And this is why you get this X shape. Look like X shapes on this as you visualize it. As you see this. Rebar engaged back to that line there. And then that's cover on the back side of its cover. So they got the development length with crossing the rebar in a lot of locations, crisscrossing. Again, this is the pad, and these are columns. I'm sorry, bracing, temporary shoring. And then they go over the column that would be, let's just put a column here. So say the column was here. Okay, remember the column has heads like that. And it engages in the deck. Ending this video because I can get, it's quite a lot of more images I can tie this all in, but I want you to visually see it. Okay, so deflection happens in the deck. It starts straining and pulling on the rebar engagement, the bond strength, it loses, it breaks, and it punctures around there, butterflying down to the middle of the deck. Beginning indicator was that fracture over here, and the one by the garage back there, the one I showed you by the planter box. I'm sorry, it's further up. Okay, so those are your indicators, that fracture there, and the planter box rotation indicating it is sagging in the deck, approximately there and further back. Loading of the vehicles, 40 years. The offset rectangular array, I often call it triangular array. That's just me, my processing of thinking. Rectangular array is what is referred to as in ACI. You can look it up. There was no skewed steel, meaning from column to column to help load support it. That skewed the offset column issue. End of this video.